In this chapter, we're going to look at what a mole is. It's a number, a way to count certain things. Specifically, we use this to count molecules. And then this idea of stoichiometry, so how we use numbers within chemical equations. We're going to look at using this idea of a mole and Avogadro's numbers to convert between molecular equations and the way that we measure things in the laboratory space. We're going to use what's called empirical and molecular formulas. We're going to discuss this and how that is done, and then we're going to determine different amounts of limiting reactants. So meaning how much, if we put something in, what thing is going to limit the amount of product we can get out, or how much unreacted substance will remain. And then finally, we're going to do some calculating of percent yields for certain reactions. All right, so the mole, what is the mole? So a simple way to think of it is if we have table salt, which is sodium chloride, and they come together in a 1-to-1 ratio by atoms, they have the same number of atoms within that compound. So if you look at something like that, we would have sodium has a mass, we know atomic mass units, it's 23 atomic mass units, and chlorine has 35.5 mass units. So if we were to take this and we have a 1-to-1 ratio, and let's say we can add these together, this idea of atomic mass units, this is how much the compound would weigh total, and it wouldn't be a 1-to-1 ratio in terms of their masses, even though there is a 1-to-1 ratio with the elements. So we're going to think about the mole helps us to connect this idea of how many things we have versus how much weight is actually there when we're measuring it out on a scale. When we look at something like carbon, which I mentioned is that foundational element that was the most abundant, they used that as the standard for defining all of the other atomic mass units of the other elements. For a mole is the number of atoms in exactly 12 grams of carbon-12, of that isotope of carbon. So it makes this really easy. It allows us to measure something out that we know exists, right? Carbon, we have a lot of this in our environment. And 12 grams of that is equal to 1 mole. 23 grams of sodium, this is the atomic mass for sodium for a typical isotope of sodium, that is equal to 1 mole of sodium. 35.5 is the approximate atomic weight of chlorine, and so that would be a mole of chlorine. So we allow our ability now, we can connect with some of the information on the periodic table with things that we want to with things that we perhaps want to be able to do in the laboratory space, to combine these in even numbers. So the next question is, when we're looking at this, why do I have this stupid image of this mole and we have a October 23rd? Well, when we look at how many atoms actually is involved in this, what is an atom of 1 mole? How many atoms of carbon are there, for example? And this is where Avogadro's number comes into play. So this is the exact number of atoms that are associated with any mole of anything. It's 6.022 times 10 to the 23rd. So a lot of times people will celebrate what's called Mole Day. Perhaps you missed it this year, maybe not, but it's October 23rd, and it at 6:02 a.m. or 6:02 p.m., the 23rd of October, we're looking at 6.022 times 10 to the 23rd. It's a way to kind of memorize this value. So a mole, this is really just a conversion unit. A mole could be anything. It could be 6.022 times 10 to the 23rd hamburger buns, beef patties, pickles, sauce, whatever, right? But it's a way that when we're going to think about, here's the analogy. If I'm going to make 1,000 hamburgers, right, I need these different ratios of elements to create all of these hamburgers that we're going to make. The same thing with a chemical reaction. If I want to make this complex molecule, I have to have all of the individual components, and I need to make sure that they match up, that we have the right number of them. And then what we can do is we can go back and use that information to figure out what kind of weight we need, right? If we're going to go to a scale in the lab and we're going to weigh out a certain compound, we need to make sure that we have equal numbers of atoms, not equal numbers of weights. So here's this little image here where we know we can make one molecule. It allows us to kind of connect this chemical reaction when we're writing out chemical reactions, but we want to transfer this and we want to upscale this to something bigger and larger that we can actually measure in the lab. And so if we're going to run a, McDonald's, for example, we need this in a number that makes sense for the volume we're going to look at. So we need to put this in pounds, right? We might have 100 pounds of buns and 250 pounds of hamburger, 10 pounds of pickles, 16 pounds of ketchup, right? And that will allow us to make the right number of hamburgers as a final product. So 1 mole is 6.022 times 10 to the 23rd of anything. It can be xenon atoms. It could be NO2 molecules, right? If you have a group of that many of anything, and whether it's an individual element or a group of things, or it can be hamburger buns or pickles or whatever, if you have that many of anything, that's 1 mole of it. We're going to use this idea now to look at different chemical equations. So here, now we're going to start to look at, I've kind of zoomed in on the periodic table to start to get this idea. And typically, remember, we're going to have, I have on this particular table, we have the element name, we have the atomic number, which is associated with how many protons there are, and then under the atomic symbol, we have the atomic mass, which is the average, right? We're taking into account the differences and the relative abundance of different isotopes. So this is accounting for the protons and the neutrons generally, right? So we have, for these compounds that I'm showing you here, if I want to have a mole of any of these, I have to measure out 4 approximately grams of helium to have a mole of helium. I need 10.8 grams of boron for a mole of boron, 12.011 grams of carbon, right? The atomic weight, this can be the atomic mass that we are relating to how many protons and neutrons are in there, but it also tells us when we're measuring these out in grams, this is how much 1 mole is. So it's that connectivity between a molecular scale kind of thing, very tiny individual atoms, to something we can actually measure in the lab space. So 12.011 grams is equal to a mole. This is our conversion factor that we're going to be using. And we're going to use all of these conversion factors on the periodic table to start solving problems. So we can use this idea of the chemical formula is going to relate that amount, and we can relate it to a single atom or single molecule, or we can relate it to a mole group. So for example, let's look at the molecule of water. In the molecule of water, there are 2 hydrogens and 1 oxygen. We can also say, if we're looking at a chemical reaction, that we have this 2 moles of hydrogen, and for every 2 moles of hydrogen, that would have to react with 1 mole of oxygen to create 1 mole of water. So this is where we're going to start using this idea of moles, that we can also say 2 molecules or 2 atoms of hydrogen plus 1 atom of oxygen will equal 1 molecule of water. This can be on the mole scale, and it can also be at the atomic scale. So we can say those same things. We're replacing the moles with atoms if it's an atom, or molecules if it's a molecule. This brings us to the idea of molecular mass. So we're going to take the atomic masses and all of the atoms in that molecule, we're going to add those up, and then we're going to get the molecular mass. So that's why in the last section we talked about we had to account for all of the atoms. And the reason we need to account for all of the atoms and be able to understand those molecular formulas is that so we can do this part. So we're going to sum up all of the atoms there. So let's look at carbon dioxide. We have carbon, which has an atomic mass of 12.011, oxygen 15.999. We're going to take 1 mole of carbon and oxygen but there are 2 of these, right? We have, with this subscript, it says we have 2 oxygen. If I add these all up, that is going to give me 44.009 grams per mole. This means grams per mole. So I can add these all up and get a molecular mass for this compound. When we look at the SI units for the amount, for looking at 1 mole, 1 mole of substance X is going to be a representative amount. So these compounds here, let's look at a mole of sulfur. All we have to do is look at the atomic mass. So that is going to be equivalent to 32.06 grams per mole. This provides for us a conversion factor now. NO2, we're going to add the different compounds that are associated with that. So we'll add that nitrogen and we'll add 2 oxygen. And so we add those, that 32 plus the 14 for the nitrogen, we're going to have 36 grams. And that is 1 mole of the nitrogen dioxide. So these are our conversion factors between grams and moles, between things that we can measure in the lab space versus things that we're going to look at on paper. All right, so I want you to take a moment to determine and calculate the molar mass for the compound C2H5COOH. So you could also write this C2H5CO2H. There's a reason it's written out like that, but we're not going to talk about that right now. Take a moment, and if you're not sure how to start, remember the first step is to account all the atoms. So count up all the carbons, all the hydrogens. Sometimes they're moved around in different spots, so make sure you have counted all of those. Find the atomic mass for each of those elements. And remember that mass means grams per mole. So this number is going to tell you how many grams of something you need to weigh on a scale to get a mole of that. So account for that, and then multiply those masses by the number of elements, and then add them all together. So hopefully you were able to determine the number, the molecular mass for that last compound. We're going to do something else now. We're going to use this idea of these conversion factors to figure out, either how many grams of something we have or how many moles. And we're going to be able to use our periodic table as something that has a whole bunch of conversion factors for us to use. So this example, how many moles of iron are in 15.34 grams of iron? So what do we need to know? What do we want to determine? We want to determine the number of moles, right? So what we're going to need to use is a periodic table to look at iron. All right, so I found a periodic table online. I'm going to click on iron, and it looks like the atomic mass is 55.84. So that is going to tell us how many grams per mole. So this is atomic mass units. It's also 55.84 grams per mole. So now that we know the atomic mass for this compound, we can use this conversion factor to solve this problem. We want to know how many moles, and what we have is 15.34 grams of iron. And we know from our conversion factor, we want to cancel out grams, so we need this. We know for conversion factors, we can flip those up and down. So we can take 1 mole of iron is equivalent to 55.84 grams of iron. The grams of iron, those units are going to cancel out. And then if we take 15.34 and divide by 55.84, we will get approximately 0.2747. And that the units are going to be moles of iron. So one thing you'll notice here, MOL, that is the shortened version of moles. Yeah, it doesn't do too much, but that is, sometimes you will see MOL as the short version, or you can write the whole word, which doesn't save you much time, but just so you're aware, MOL is the same as moles. So molarity, this is what is used in science to create concentrations of a lot of different liquids. It is almost always used. And sometimes you'll have grams per milliliter, but more frequently, everything is calculated in molarity. So you'll have certain concentrations of salts or acids or bases in your solutions that you're working with. And that is typically how these things are done. So you'll have pH balance, and you'll say, we had to add so many moles of acid or base or salt in our reagent. So it is very common way that we're going to do measurements in science. All right, so I'm going to have you guys do a problem here where you're going to calculate if we need 0.168 moles of calcium phosphate for an experiment, how many grams do we need to weigh out? So this you should be able to complete on your own. I'm going to remind you that what do we need to determine? So look at every time you're kind of solving these problems, what is it that your outcome is going to be? We want grams, right? So that grams is going to be really important because you will need to find a conversion factor that is going to provide grams for you. What do we have? We will have, our starting point is going to be, we have 0.168 moles of calcium phosphate. And the end point, we want grams of calcium phosphate. And then in the middle here, right, we need our conversion factor. And how we're going to determine that, we've already walked through the steps, right, for determining the molecular weight or the molecular mass, and that should be calculated in grams per mole, right? That's going to be our conversion factor for solving this problem. Okay, one more practice problem here in terms of the calculations. How many moles of carbon dioxide are there in 10 grams? So you'll have to determine the molecular mass in grams per mole. Use that conversion to solve for how many moles are in 10 grams. One final problem. Grams of platinum are in 0.475 moles of platinum. So these should all be pretty easy. If they're not and you're still struggling with this, please let me know and we can walk through some more examples like this. But I would like you to post your answers in our Blackboard space. We're going to use molarity to really get a hold on what we can actually measure in the lab space. And it allows us to look at and connect the grams of something, and we use that molar mass as a conversion factor to give us the moles of something. And then Avogadro's number is another conversion factor that allows us to transport between moles and then the number of atoms or molecules we have. So this idea here is an important concept that, and where these arrows are essentially conversion factors, and then these blocks in here are different units that are basically telling us, things that we can measure. Again, let's go back and kind of look at some of these questions where we want to determine something that we're going to change this to how many. So before the last examples, we were looking at how many silver molecules. We were looking at how many moles before we were looking at. Now we want the number of atoms. So this is different, and we're going to have to use some other information, some other conversion factor to figure this out. So what is it that we're trying to determine? We want atoms, right? And then what do we know? Well, one thing that we do know, we know that we have 85.0 grams of silver. And then we know that we're going to have to figure out the atomic mass for this compound. The atomic mass is going to be 107.87 grams of silver per 1 mole of silver. Now, if I leave this on the top, I'm going to get grams of silver squared, right? If I multiplied this by 107.87 grams of silver over 1 mole, I'm going to get, this is going to multiply with itself, and then my answer is going to be grams of silver squared, which doesn't make sense. So let's not do that. How do we fix that? Remember, we need to put this stuff up. In order to fix that, we're going to have to switch these around. Remember, 1 mole of silver is equal to 107.87 grams. Those are conversion factors. They can be flipped upside down because they are equal to 1. And when that is true, then that means that it doesn't matter what's on the top or the bottom of that ratio. So 1 mole of silver is equivalent to 107.87 grams of silver. And our silver cancels out, or grams of silver cancels out. We'll get moles of silver out. All right. I don't want the number of moles, though. I want the number of atoms. This is where we use Avogadro's number. So I'm not going to solve this yet. I'm going to go to the next step. I'm going to add a step in here. How do I get from moles of something to the number of atoms? Remember, there's that magic number 6.022 times 10 to the 23rd of something, of anything, is equal to 1 mole. So I can make another ratio. 1 mole of anything is equal to 6.022 times 10 to the 23rd. And in this case, it's going to be, we're going to have atoms of silver. So now our moles of silver cancel out, and we're left with atoms of silver. That should give you, if you multiply, we're going to multiply 85 times 6.022 times 10 to the 23rd. Divide all of that by 107.87, and that should give you something close to 475 times 10 to the 23rd atoms of silver. All right. I have one final experiment for you to look at and to think about. There was actually a student in a high school that sued their teacher because he asked them to do what I'm going to ask you to do. He eventually lost because the teacher, he thought it was an unfair assignment. He ended up losing the lawsuit because the judge ruled in the favor of the teacher because he thought he wasn't given enough information to solve the problem. The problem was the instructor asked the students to determine how many atoms of aluminum there would be in a roll of aluminum foil. For this experiment, I want you to think about what information would you need to know to determine how many atoms of aluminum are in a roll of aluminum foil? What information do you need to know about that roll? What I want you to do as an assignment is then find that information that you need to know. So find a roll of find a roll of aluminum foil and then write that information down. And then I want you to determine the number of atoms in that roll of foil. We may have to have a conversation about what information you need and how to find it. But I want you to start to think about what information you would need in order to determine this and collect as much as you can. If you can't figure this out, determine as much as you can, and then we'll kind of have a conversation about how this would be solved. And that's kind of the end of this section, and then we'll continue on talking more about the stoichiometry and using chemical equations and the molarity idea to start to make connections between when we have chemical reactions occur, how much we need, how much we get out, how much product is formed, all of that fun stuff.